Hi, my name is Krutik Alapati, and here's my presentation on Lab 5 for Faraday's Law. The purpose of this lab is to create a simulation of a bar magnet falling through a conductive metal tube and compare the results to a simulation of the same experiment on a computer to better understand Faraday's Law and the effects of induced current. So the results showed that the time predicted by the computer simulation was slightly larger at 1.15 than the average times from the experiment, which was 1.18 seconds. The percent error between the experiment and simulation was 2.78. So the concepts and formulas we'll use in this experiment are, to begin with, magnetic fields, magnetic flux, Newton's second and third law, and then we'll use Lenz's law, the Biot-Savart law, Faraday's law, and Ohm's law. And the last four can be seen in the order listed on the right side of the screen. The initial conditions in experimental design were that the system was the magnet in the aluminum tube, and the surroundings were the universe surrounding the magnet and tube. So the model was that a magnetic dipole in the form of a bar magnet was dropped into the aluminum foil tube, which is conductive and non-ferrous, with the north pole facing down and towards the tube. The time for the magnet to reach the other side was recorded 5 times and then averaged. The assumptions made were that there's no air resistance, and the only forces acting on the system were the magnetic and gravitational forces, and that the bar magnet acted as a dipole. The initial conditions were that the magnet was dropped from rest. Here I have the measurements I recorded, which were that the length of the tube was 0.3 meters, the width was 0.007 meters, the inner radius was 0.017 meters, and the radius was 0.024 meters. The magnetic dipole moment was taken from Lab 3, which was 2.105 amperes meters squared, and the mass of the magnet was 0.025 kilograms. You can see the 5 trials on the right, and the average time was 1.118 seconds. So why can't we use a ferrous tube? Well, the magnetic properties of iron in the material would cause an induced magnet and interfere with the magnet. And what happens to the magnet, and how does it compare to the magnet falling in free space? The magnet slows down while falling in the tube, likely due to an induced current putting force on the magnet, and the magnet falls quicker in free space. Here you can see my glow script code. On the top left, you have the initial values for the system, and then below that you have the initiation of the graph, and then below that you have the measurements made from part 1. And then the bottom left code shows the mass of the magnet, the magnetic moment from Lab 3, and below that the visualization of the bar magnet, as well as the initial conditions. And on the right side you can see the function used to calculate the magnetic field, and then below that you can see the function used to calculate the magnetic flux. So for the second part of the glow script code, on the left you can see that there's a line to calculate the gravitational force on the magnet, and then you can see that there is a line to calculate the current on the aluminum foil, and below that, since there should be 2 currents, you have the calculation of the B field at each of those currents. And then on the right side you have the magnetic force on the magnet, and then the net forces on the magnet, and then below that you have the updating code for the velocity and position of the bar magnet. And here you can see on the model, you can see the 2 currents generated while the magnet's falling on the aluminum foil on the left, shown in blue and red. And then you have the velocity versus time graph on the right, showing how the velocity changed as the magnet fell through the tube in the simulation. So interpreting the simulation, which color represents the clockwise current and which color represents the counterclockwise current as viewed from above? Well, using Lenz's law, you can determine that red corresponds to the counterclockwise, and the blue corresponds to the clockwise in this simulation. And what happens to the dynamics of the system if you flip the magnet around? Well, the direction of the currents and forces would also be flipped, but the magnet would still be slowed down, and the net force would stay the same after. So how does the time and tube of the real world system compare to that of the computational system, and how might the computational system be made more accurate? Well, the magnet in my experiment fell slower in real life than in the computer simulation, so the simulation could be made more accurate by accounting for air resistance. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The forces acting on the magnet were initially different in magnitude. However, after a short period of time, the forces balanced out, and the velocity of the magnet remained constant. So their error was 2.78%, and this could be due to human error in measuring the time or air resistance not being taken into account. And the magnetic moment from lab 3 could be different than the originally calculated magnetic moment. If the resistivity of the conductor were reduced as close as possible to zero, the force from the induced current from the magnet falling would increase until the magnet stopped moving. If the tube had holes or slots cut into it, this would decrease the flow of total current in the tube, and due to this, the force from the induced current would be lower and the magnet would fall quicker.